Hello there, and welcome. Tonight, we embark on a quiet journey through one of the most beautiful concepts in all of astronomy, the light year, a measure not of time, but of distance, a bridge between the vast cosmos and our small corner of existence. As you settle in, let your breathing slow, your thoughts quiet, and allow yourself to drift through the wonder of light itself. If you find comfort in these peaceful explorations, I invite you to like and subscribe, or leave a gentle thought in the comments below. It helps others discover this sanctuary of calm learning, one sleepy soul at a time. But for now, all you need to do is rest, breathe deeply, and let the story of light years carry you softly into the night. What is a light year? A light year is not a measurement of time, despite what its name might suggest. It is a distance, the distance that light travels in one full year as it races through the vacuum of space. Light moves faster than anything else in the universe, streaming forward at nearly 300,000 kilometers per second. That is 7 times around Earth's equator in just 1 second. In a single year, light travels nearly 10 trillion kilometers, or about 6 trillion miles. This vast distance is what we call a light year. It is the ruler astronomers use to measure the incomprehensible gulfs between stars. When we say a star is 10 light years away, we mean the light we see tonight left that star 10 years ago, traveling without pause across the darkness to reach our eyes. Every point of light in the sky carries with it not just beauty, but a story written in distance and time. The concept seems simple at first. Light travels far in a year, but when you pause to consider what this truly means, the implications unfold like petals of a cosmic flower. The universe speaks to us, not in the present, but in echoes from the past. Every glance upward is a look backward through time itself. The speed of light is constant. Light always travels at the same speed through empty space. This is one of the fundamental truths of our universe, discovered and proven through countless experiments. Whether light comes from a distant galaxy or a candle in your hand, it moves at exactly the same pace through the void, 300,000 kilometers per second, not approximately. Exactly. This constancy is remarkable. It does not matter if the source of light is moving toward you or away from you. The light itself always arrives at the same speed. This strange and wonderful fact became the foundation of Einstein's theory of relativity, reshaping our understanding of space, time, and reality itself. The steadiness of light became the one fixed point in a universe where everything else proved flexible. Because light never changes its pace, we can use it as a perfect measuring stick. If we know how fast light travels, and we know how long it has been traveling, we can calculate exactly how far it has come. This is how astronomers measure the universe, not with physical rulers stretched across space, but with the patient journey of photons crossing the dark. When you look at a star and learn it is 100 light years away, you are learning that its light has been traveling toward you for a full century. That photon began its journey long before you were born, perhaps before your grandparents were born, streaming silently through space until it finally reached your eye. In that moment, the past and present touch. Light from the sun takes 8 minutes to reach Earth. The sun, our closest star, sits about 150 million kilometers away. That seems impossibly far, and yet in cosmic terms, it is nearly touching us. The light from the sun's surface takes just over 8 minutes to cross that distance and warm our world. This means that when you step outside and feel sunlight on your skin, you are feeling light that left the sun 8 minutes ago. If the sun were to suddenly vanish, we would not know it for 8 minutes. The sky would remain bright, the warmth would linger, and life would continue as though nothing had changed. Only after those 8 minutes would darkness fall. This thought experiment reveals something profound. We never see the sun as it is right now. We only see it as it was, 8 minutes in the past. The same is true for everything else in the universe, but the delays grow longer. The moon's light, reflected sunlight, reaches us in just over 1 second. When astronauts walked on the lunar surface, their radio transmissions took that same second to travel back to Earth, creating a strange conversational delay. But the moon is our neighbor. The stars are far more distant. Even light's incredible speed becomes almost slow when faced with the vastness of space. 8 minutes to cross from the sun to Earth, years to reach us from the nearest stars, millennia to arrive from distant galaxies. The universe is so large that even light, the fastest thing there is, must labor across it like a traveler on an endless road. The nearest star beyond the sun is over 4 light-years away. Proxima Centauri is the closest star to our solar system beyond the sun itself. This small, faint red dwarf lies just over 4 light-years away. In cosmic terms, this is practically next door. But consider what 4 light-years truly means. The light you see from Proxima Centauri tonight left that star over 4 years ago. It has been traveling through empty space all that time, racing toward us at the speed of light without rest or pause. If you could somehow travel at the speed of light, which is impossible for anything with mass, it would still take you 4 years to reach Proxima Centauri, and that is our nearest neighbor. The next closest star system, Alpha Centauri, is slightly farther at about 4.4 light-years. These stars are so far away that no human has ever seen them move, except through careful astronomical measurements over decades. Imagine trying to reach Proxima Centauri with current technology. Our fastest spacecraft, Voyager 1, travels at about 17 kilometers per second. That sounds fast, and it is by human standards. But even at that speed, it would take over 70,000 years to reach Proxima Centauri. Light makes the journey in just over 4 years. This is the vast gulf between light's speed and our own capabilities. The stars that look so close in the night sky, clustered together in constellations, are separated by distances so enormous that light itself must travel for years between them. The neighborhood of stars surrounding our sun extends for dozens of light-years in all directions, each one a distant sun, each one unreachably far by any means we currently possess. Sirius, the brightest star, is 8.6 light-years away. Sirius blazes in our winter skies, impossible to miss. It is the brightest star visible from Earth, outshining all others with its blue-white brilliance. Ancient civilizations watched it rise and set, tying their calendars to its movements. The Egyptians linked it to the flooding of the Nile. The Greeks associated it with the heat of summer, giving us the phrase dog days. But Sirius, for all its brilliance, is not particularly close. It lies 8.6 light-years away. The light you see from Sirius tonight began its journey over 8.5 years ago. If you had looked at Sirius on the day you were born, you would have seen light that left the star years before your birth. Every glance at Sirius is a glance backward in time. Sirius appears so bright, not only because of its distance, but because it is intrinsically luminous. It shines over 20 times brighter than our Sunday. If you could somehow replace the sun with Sirius, Earth would be bathed in intense light and heat, far beyond what life could endure. But from 8.6 light-years away, Sirius is a beautiful jewel, brightening our winter nights without threat. The system is actually a binary, 2 stars orbiting each other. The companion, Sirius B, is a white dwarf, the dense remnant of a star that exhausted its fuel and collapsed. It orbits Sirius A every 50 years, invisible to the naked eye, but revealed through telescopes. Two stars, dancing together, their light reaching us across nearly 9 years of travel through the void. Polaris is 430 light-years distant. Polaris, the North Star, has guided travelers for millennia. Sitting almost exactly above Earth's North Pole, it marks true north in the sky with remarkable precision. Sailors, explorers, and wanderers have looked to Polaris for direction, trusting its steadfast position. But Polaris is not close. It lies approximately 430 light-years away. This means the light you see from Polaris tonight left that star over 4 centuries ago. When that light began its journey, the year was around 1600. Shakespeare was still writing his plays. Galileo was beginning his telescopic observations. The world was vastly different, and yet the light from Polaris has been traveling toward us all this time, finally arriving tonight to guide your gaze. Polaris is not a single star, but a multiple star system. The primary star, Polaris A, is a supergiant, far larger and brighter than our Sunday. 2 smaller companions orbit it. Through telescopes, astronomers can detect them and study their movements. But to the naked eye, Polaris appears as one steady point, a beacon in the north. The star is also a Cepheid variable, pulsing slightly in brightness over a period of days. These pulsations are subtle, barely noticeable without instruments, but they make Polaris scientifically valuable. Cepheid variables are used to measure cosmic distances, their pulsation periods, revealing their intrinsic brightness. Polaris, the faithful guide star, is also a cosmic measuring stick. Betelgeuse may already be gone. Betelgeuse, the red supergiant marking Orion's shoulder, is one of the most recognizable stars in the sky. Its ruddy glow stands out among the blue-white stars surrounding it. But Betelgeuse is not just colorful, it is enormous, a dying star swollen to hundreds of times the diameter of our Sunday. If placed at the center of our solar system, its surface would extend past the orbit of Mars. Betelgeuse lies approximately 600 light-years away. This means the light we see tonight left the star around the year 1400, medieval times on Earth. Kingdoms rising and falling, explorers beginning to chart the world. And all that time, light from Betelgeuse has been streaming toward us through space. Here is the unsettling thought. Betelgeuse is nearing the end of its life. Astronomers know it could explode as a supernova at any time. Any time in cosmic terms means it might have already happened. The star could have collapsed and exploded centuries ago, but the light from that explosion would still be on its way to us. We would not know until the light arrived. If Betelgeuse has already gone supernova, we will not see it until the light from that event completes its 600-year journey. When it does arrive, if it does, the explosion will be visible even in daylight, a brilliant new star appearing suddenly in Orion. For weeks or months, it will outshine everything except the sun and moon, a beacon announcing the death of a star that actually occurred centuries ago. The Andromeda galaxy is 2.5 million light-years away. The Andromeda galaxy, our nearest large galactic neighbor, is visible to the naked eye under dark skies. It appears as a faint, fuzzy patch, easily overlooked if you do not know where to look, but that pale smudge is extraordinary. It is an entire galaxy, containing perhaps 1 trillion stars, and it lies 2.5 million light-years away. Think carefully about what this means. The light you see from Andromeda tonight began its journey 2.5 million years ago. When that light left Andromeda, humans did not exist. Our earliest ancestors were just beginning to diverge from other primates. The Earth was in the grip of the Pleistocene epoch, Ice ages came and went. Species evolved and vanished. And all that time, light from Andromeda was crossing the intergalactic void toward us. The ancient photons that reach your eyes tonight have been traveling for longer than human civilization has existed, longer than Homo sapiens has walked the Earth. They have crossed a gulf of space so vast that it contains essentially nothing. No stars, no planets, just emptiness. And yet the light kept moving, patient and steady, at 300,000 kilometers per second, every second, for millions of years. When you see Andromeda, you are not seeing it as it is now. You are seeing it as it was when saber-toothed cats prowled the Earth. The galaxy you observe is ancient history, a snapshot from deep time. The Andromeda of today, the Andromeda that exists right now, is unknowable to us. We will not see it for another 2.5 million years. Every star in the night sky shows us the past. This truth applies to every point of light above you. The stars of the Big Dipper, forming that familiar pattern, range from 80 to 120 light-years away. Their light left them in the early 20th century. The brilliant star Vega, which will one day serve as Earth's North Star thousands of years from now, lies 25 light-years distant. Its light began traveling in the late 1990s. Even the planets, which seem close because they shine so steadily and brightly, show us the past. Jupiter's light takes about 40 minutes to reach us when the planet is at its closest. Saturn's takes over an hour. Mars, when near, sends its light to us in just a few minutes. But still, that light is old. What you see is not what is, but what was. The night sky is not a photograph of the present universe. It is a collage of the past, with each star contributing light from its own moment in history. Some stars show us decades ago, others show us centuries. The farthest galaxies visible through powerful telescopes show us billions of years ago, light from a time when the universe itself was young. The sky is a time machine, visible to anyone who looks up. This is why astronomers speak of looking back in time when they observe distant objects. They are not being poetic, they are being literal. To observe something 10 light-years away is to see it as it was 10 years ago. To observe something 10 billion light-years away is to see the universe as it was 10 billion years ago, long before our Sun or Earth existed. Light-years reveal the universe's history. Because light takes time to travel, and because the universe is so vast, the light reaching us from different distances shows us different epochs. Nearby stars show us the recent past. Distant galaxies show us the ancient past. By observing objects at different distances, astronomers assemble a history of the universe, stretching back billions of years. The most distant objects ever observed lie over 13 billion light-years away. Their light has been traveling toward us for most of the age of the universe itself. These galaxies appear as they were when the cosmos was young, when the first generations of stars were igniting, when structure was just beginning to form. They are fossils of light, preserved messages from cosmic dawn. Studying these distant objects reveals how galaxies have changed over time. Early galaxies were smaller, more chaotic, filled with intense star formation. Over billions of years, they merged and grew, settling into the majestic spirals and ellipticals we see in the nearby universe. By comparing galaxies at different distances, and therefore different times, astronomers watch evolution unfold. This is the gift of light years. They give us access to history. On Earth, we study the past through fossils, ancient ruins, and written records. In astronomy, we study the past through light. The universe preserves its own history, in the photons streaming across space, arriving at our telescopes as archives of what once was. Every observation is an act of time travel. The observable universe is bounded by light. There is a limit to how far we can see, and it is defined by the speed of light. The universe is approximately 13.8 billion years old. This means light has had 13.8 billion years to travel toward us since the Big Bang. Any light from farther away simply has not had time to reach us yet. The distance light can travel in the age of the universe defines the observable universe. This creates a sphere around us, roughly 93 billion light-years in diameter. Wait, how can it be larger than 13.8 billion light-years if light has only been traveling for 13.8 billion years? The answer lies in the expansion of space itself. While light has been traveling toward us, space has been stretching, carrying distant objects even farther away. The observable universe is therefore larger than you might expect. But beyond this boundary, we cannot see. Not because there is nothing there. In fact, we assume the universe extends far beyond what we can observe, perhaps infinitely. But the light from those regions has not yet reached us. It is still on its way and may never arrive if the universe continues to expand faster than light can cross it. There is an entire cosmos beyond our horizon, forever hidden. This boundary is not a physical edge. It is simply the limit of information. Light carries information, and if the light has not arrived, the information has not arrived. We are surrounded by a sphere of knowable space, and everything beyond it is unknowable, at least for now. The observable universe is both vast and limited, a paradox written in light years. Expansion stretches light on its journey. As light travels through space, space itself expands. This expansion stretches the light, shifting it toward longer, redder wavelengths. Astronomers call this redshift, and it is one of the most important discoveries in cosmology. The farther light travels, the more space expands during its journey, and the more redshifted it becomes. By measuring redshift, astronomers can determine how far away an object is. Light from nearby galaxies shows little redshift. Light from distant galaxies shows dramatic redshift, sometimes stretched so much that ultraviolet light becomes visible red or even infrared. This stretching is not caused by the motion of galaxies alone, though galaxies do move. It is caused by the expansion of the universe itself, pulling space apart and carrying galaxies with it. Redshift tells us not just distance, but also age. The more redshifted a galaxy appears, the farther away it is, and therefore the longer its light has been traveling, and therefore the farther back in time we are seeing it. Redshift becomes a clock, measuring the age of the light and revealing when the photons began their journey. It is a beautiful connection between distance, time, and the structure of space. This stretching also affects the energy of light. Redshifted light has less energy than it did when it was emitted. The universe saps energy from photons as they travel across expanding space. By the time ancient light reaches us from the edge of the observable universe, it has been stretched and cooled, arriving faint and tired after its unimaginably long journey. Some light will never reach us. The expansion of the universe is accelerating. Distant regions of space are moving away from us faster and faster, driven by a mysterious force astronomers call dark energy. For the most distant galaxies, space is expanding so rapidly that their light is being carried away faster than it can move toward us. This light will never reach Earth. There are galaxies whose light left them billions of years ago, racing toward us at the speed of light. But the space between us and them is expanding faster than light can cross it. The photons make progress, but the finish line keeps moving away. They are like runners on a treadmill set too fast. They can never catch up. This light is lost to us, forever receding into the unreachable distance. As time goes on, more and more galaxies will cross this boundary. Billions of years from now, the observable universe will shrink. Galaxies that we can see today will have moved so far away, accelerated by expansion, that their light will no longer reach us. Future astronomers, if they exist, will see a lonelier universe, with fewer galaxies visible in their skies. This is one of the profound truths about light years and cosmic distances. Not all of the universe is accessible to us. Not all of its light will ever arrive. There are events happening right now in distant regions whose light is moving toward us but will never complete the journey. The universe has secrets it will never share, hidden forever beyond the accelerating horizon. Light from the cosmic microwave background is the oldest we can see. The oldest light in the universe comes from the cosmic microwave background, the afterglow of the Big Bang itself. This light was released about 380,000 years after the universe began, when it cooled enough for atoms to form and light to stream freely through space. That light has been traveling ever since, stretched by expansion into microwaves, and it fills the entire sky. The cosmic microwave background is not from a specific location. It is from everywhere. In the early universe, space itself was glowing, filled with hot plasma. As the cosmos expanded and cooled, that glow faded into the background radiation we detect today. Measuring this light, astronomers have mapped tiny temperature variations that reveal the seeds of galaxies, the density fluctuations that eventually grew into the structure we see today. This light has traveled for over 13 billion years to reach us. It is the oldest light we can observe, a message from the universe's infancy. Before this time, the universe was opaque. Light could not travel freely because it was constantly absorbed and re-emitted by the dense plasma filling space. The cosmic microwave background marks the moment the universe became transparent, the dawn of the age of light. To detect this ancient glow is to touch the beginning of time itself. Telescopes tuned to microwave frequencies capture photons that have been traveling since shortly after creation. Every direction we look, we see this faint radiation, the same everywhere, a uniform whisper from the past. It is the furthest back we can see using light. Before this, there is only theory and mathematics. Neutrinos travel at nearly the speed of light. Light is not the only messenger from the cosmos. Neutrinos, nearly massless particles, also stream through space at speeds close to the speed of light. Unlike photons, neutrinos barely interact with matter. They pass through entire planets as though nothing is there. Trillions of them pass through your body every second, unfelt and unseen, racing onward without pause. Neutrinos are produced in the hearts of stars, in supernovae, and in other energetic events. Because they interact so weakly, they escape from regions where light cannot. When a massive star collapses and explodes, neutrinos burst free hours before the light does, carrying the first news of the catastrophe. Detectors on Earth, buried deep underground to shield them from other particles, can catch these ghostly messengers. In 1987, neutrinos from a supernova in the Large Magellanic Cloud were detected on Earth, arriving hours before the light. The supernova, called SN 1987A, was visible to the naked eye and studied intensely. But the neutrinos brought earlier confirmation, traveling 168,000 light-years across space, proof that neutrinos carry information just as light does, if we have the instruments to capture them. Neutrino astronomy is still in its infancy, but it promises new ways of exploring the universe. Because neutrinos travel at nearly light speed and pass through matter, they can reveal processes hidden from light. Observing the universe through neutrinos is like listening to a symphony through a different instrument. The same events, the same sources, but a new perspective, a new understanding. Gravitational waves also travel at the speed of light. In 2015, humanity detected gravitational waves for the first time. These are ripples in the fabric of spacetime itself, caused by violent events like colliding black holes or neutron stars. Gravitational waves travel at the speed of light, spreading outward from their source like ripples on a pond. But instead of moving through water, they move through space itself, stretching and compressing it as they pass. Einstein predicted gravitational waves a century earlier, but they are so faint that detecting them requires extraordinary precision. The LIGO and Virgo observatories use laser beams and mirrors, separated by kilometres, to measure distortions in space smaller than a fraction of the width of a proton. When a gravitational wave passes through Earth, it briefly stretches space in one direction and compresses it in another, a subtle flexing of reality itself. The waves detected in 2015 came from two black holes colliding over 1 billion light-years away. The event happened a billion years ago. The gravitational waves, traveling at light speed, took a billion years to reach us. When they arrived, they carried information about those black holes, their masses, their spins, the way they spiraled together before merging. It was the first time humans heard the universe in this way. Gravitational wave astronomy opens yet another window on the cosmos. Light shows us glowing objects. Neutrinos show us nuclear processes. Gravitational waves show us the motion of massive objects and the warping of space-time itself. Each travels at or near the speed of light, carrying information across vast distances. Together, they give us a richer, deeper understanding of the universe and its many voices. Fast radio bursts cross billions of light-years in milliseconds. Among the strangest signals astronomers detect are fast radio bursts. These are intense blasts of radio waves that last only milliseconds. Despite their brief duration, they release as much energy as the sun emits in days. They appear randomly across the sky, flashing once and usually vanishing forever. Some sources have been observed repeating, but most remain mysterious. Fast radio bursts come from far away, often billions of light-years distant. This means the signals we detect today were emitted billions of years ago. Something in the distant universe produced a brief, violent pulse of energy, and that pulse has been traveling toward us ever since. When it arrives, our radio telescopes catch the signal, a fleeting whisper from across the cosmos. What causes these bursts? Astronomers are still investigating. Leading theories involve magnetars, neutron stars with incredibly powerful magnetic fields, or perhaps colliding neutron stars, or even more exotic possibilities. Each burst carries information encoded in its radio waves, clues about the environment it passed through, the distance it traveled, and the event that created it. Fast radio bursts remind us that the universe is full of phenomena we do not yet understand. Despite decades of studying the sky, new mysteries continue to emerge. These bursts, traveling billions of light-years to reach us, are messages from the distant universe, puzzles waiting to be solved. They show that light and other electromagnetic waves are still revealing secrets, still teaching us, still surprising us. The Hubble constant measures the expansion rate. Astronomers measure the expansion of the universe using the Hubble constant, named after Edwin Hubble, who discovered that distant galaxies are moving away from us. The Hubble constant tells us how fast space is expanding. It relates the speed at which a galaxy is receding to its distance from us. The farther away a galaxy is, the faster it appears to be moving. This relationship is revealed through redshift. By measuring how much a galaxy's light is redshifted, astronomers determine its velocity. By measuring its distance, often using Cepheid variable stars or supernovae as standard candles, they establish how far away it is. Plotting velocity against distance reveals a straight line, the Hubble law. The slope of that line is the Hubble constant. The value of the Hubble constant is still debated. Different measurement methods yield slightly different results, a puzzle called the Hubble tension. But the concept is clear. The universe is expanding, and the rate of expansion determines how light years relate to time. A galaxy 1 billion light-years away is not just 1 billion light-years distant in space, it is also receding from us, carried by the expansion itself. This expansion means the universe was smaller in the past and will be larger in the future. Running the clock backward, we reach a moment when all matter was condensed into an unimaginably hot, dense state. That moment is the Big Bang, the beginning of space, time, and light itself. The Hubble constant helps us calculate the age of the universe and understand its history. Light years connect distance and time inseparably. In everyday life, distance and time are separate. You can travel a certain distance in a certain time, but one does not define the other. In the cosmos, for light, distance and time are intertwined. A light year is simultaneously a measure of space and a measure of time. To say something is 100 light years away is to say its light has been traveling for 100 years. This connection is profound. It means the farther we look into space, the farther back in time we see. Astronomy is inherently historical. Every observation is an observation of the past. Nearby objects show us the recent past. Distant objects show us the ancient past. There is no way to see the present state of a distant star or galaxy. We are forever looking backward, constrained by the speed of light. This also means the universe has depth in time as well as space. When we map the cosmos, we are not just mapping locations, we are mapping moments in history. A three-dimensional map of galaxies is also a timeline, with distance corresponding to age. The universe unfolds before us like a flower, each petal a different era, all visible simultaneously because light from different distances arrives together. This is why light years are so important. They are not just convenient units for measuring cosmic distances. They are the language of cosmic time, the way we speak about the history of the universe. Without light years, we could not discuss the age of starlight, the evolution of galaxies, or the journey of photons across the void. Light years give us the vocabulary to understand our place in a vast, ancient cosmos. Understanding light years humbles us. To truly grasp the meaning of a light year is to feel smallness and wonder in equal measure. The distances involved are so enormous that they defy intuition. A single light year is nearly 10 trillion kilometres. The nearest star beyond the Sun is over 4 light-years away. The galaxy we live in stretches 100,000 light-years across. The observable universe extends for 93 billion light-years. We are tiny, brief creatures on a small world, orbiting an ordinary star in a corner of a galaxy containing hundreds of billions of other stars, in a universe containing hundreds of billions of galaxies. The light we see tonight has traveled unimaginable distances across emptiness so vast that even moving at the ultimate speed, it takes years, centuries, or eons to cross. And yet, that light reaches us. It arrives faithfully, carrying information, telling stories, connecting us to distant places and ancient times. We are not separate from the cosmos. We are part of it, made of the same matter, governed by the same laws, bathed in the same ancient light. The photons that strike our eyes tonight have traveled farther than any human will ever go, and yet they end their journey here, with us. To understand light years is to understand both our insignificance and our connection. We are small, yes, but we are also observers, thinkers, beings, capable of measuring the universe and contemplating our place within it. The vastness that humbles us also invites us to wonder, to explore, to seek understanding. Light years are the map to that exploration, the guide to the immense and beautiful cosmos we call home. Measuring cosmic distances takes ingenuity. How do astronomers know how far away stars and galaxies are? We cannot stretch a measuring tape across space. We cannot travel to distant stars and back. Instead, astronomers have developed a cosmic distance ladder, a series of methods that build upon each other, each one reaching farther than the last. At its foundation is the speed of light, constant and reliable. For nearby objects within our solar system, we use radar. Radio waves sent to planets or asteroids bounce back, and by measuring the time delay, we calculate distance. Light travels at a known speed, so time equals distance. Venus, Mars, and the Moon have all been measured this way with extraordinary precision. This gives us the first rung of the ladder. For nearby stars, we use parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. This shift, measured in tiny fractions of a degree, reveals distance through geometry. The closer a star, the larger its parallax. The Gaia spacecraft has measured parallax for over 1 billion stars, mapping our galactic neighborhood with unprecedented accuracy. Beyond parallax, astronomers use standard candles, objects whose intrinsic brightness is known. Cepheid variable stars pulse with periods related to their luminosity. By measuring the period and comparing the star's apparent brightness to its known intrinsic brightness, distance can be calculated. This method works for stars millions of light-years away, reaching into nearby galaxies. Supernovae serve as cosmic lighthouses. For even greater distances, astronomers use Type Ia supernovae. These are explosions of white dwarf stars that have accreted too much mass from a companion star, triggering a runaway nuclear reaction. Type Ia supernovae always explode with roughly the same intrinsic brightness, making them excellent standard candles. They are so luminous, they can be seen across billions of light-years. By observing Type Ia supernovae in distant galaxies and comparing their apparent brightness to their known intrinsic brightness, astronomers determine how far away those galaxies are. This method revealed one of the most surprising discoveries in cosmology. In the late 1990s, two independent teams studying distant supernovae found that the universe's expansion is accelerating, driven by dark energy. These supernovae, billions of light-years away, showed us that the cosmos is not just expanding, it is expanding faster and faster. The light from these explosions, traveling for billions of years to reach us, carried information about the state of the universe when they occurred. By measuring many supernovae at different distances and therefore different times, astronomers traced the expansion history of the universe. Each supernova is a brief beacon, flaring brilliantly before fading away. But in that brief moment, it illuminates the vast darkness, telling us how far it is, how long its light has traveled, and what the universe was like when the explosion occurred. These cosmic lighthouses guide us through the deepest reaches of space and time, their light-years of travel bringing us knowledge. Redshift extends our view to the edge of the observable universe. For the most distant objects, beyond the reach of standard candles, astronomers rely on redshift alone. By measuring how much a galaxy's light has been stretched, they infer how far away it is and how long the light has been traveling. The relationship between redshift and distance is well understood through the equations of cosmology, grounded in general relativity and observations of the universe's expansion. The most distant galaxies ever observed have redshifts greater than 10. Their light has been stretched so much that what was once ultraviolet or visible light is now detected as infrared. These galaxies appear as they were over 13 billion years ago, less than a billion years after the Big Bang. Their light has been traveling for most of the age of the universe itself. Observing these distant galaxies requires powerful infrared telescopes. The James Webb Space Telescope, launched in 2021, is specifically designed for this purpose. Its large mirror and sensitive instruments can detect faint, redshifted light from the earliest galaxies, revealing the universe's infancy. Each discovery pushes our view deeper into the past, closer to the beginning. Redshift connects wavelength, distance, time, and the expansion of space into a single, elegant relationship. By measuring the color of light from a distant galaxy, astronomers can determine not just where it is, but when it is. They see not just location, but history. Light years become years of history, written in the shifting spectrum of ancient photons. The cosmic distance ladder is built on light. Every method in the cosmic distance ladder ultimately relies on light. Radar uses radio waves, which are light at long wavelengths. Parallax measures the positions of stars by their light. Standard candles compare the intrinsic and apparent brightness of light. Redshift measures how light has been stretched. Light is the messenger, the courier, carrying information across the void. Without light, we would be blind to the universe beyond our solar system. We would know nothing of stars, galaxies, or the cosmos. Light bridges the gap between us and everything else, traveling faithfully at its constant speed, arriving bearing news from distant realms. The fact that light takes time to travel, that distance and time are linked, is not an obstacle, it is a gift. Because light takes time, we can see the past. Because different distances mean different travel times, we can observe the universe at many different ages. The sky becomes a living museum, displaying the history of creation from the present back to nearly the beginning. Every glance upward is a journey through time, guided by the ancient photons completing their long voyages. Astronomers often speak of looking deep into space, but deep also means back. The two are inseparable. To peer 13 billion light-years into space is to peer 13 billion years into the past. The deeper we look, the farther back we see. Light-years are the thread connecting here and now to there and then, stitching together a narrative that spans billions of years. Light-years show us galaxies in their youth. When we observe galaxies billions of light-years away, we are seeing them as they were in their youth. These galaxies are smaller, more chaotic, and filled with intense star formation. They do not yet have the graceful spiral arms or smooth elliptical shapes of nearby mature galaxies. They are still assembling, growing through mergers and collisions, forging the first generations of stars. Comparing these young galaxies to older ones nearby, astronomers trace the evolution of galaxies over cosmic time. They see how structure emerges from chaos, how stars form and die, how galaxies interact and merge, and how the universe transforms from a uniform sea of matter into the rich tapestry of structure we observe today. Light years are the timeline on which this story unfolds. Each light year of distance corresponds to a year of time. Observing a galaxy 10 billion light-years away means seeing it as it was 10 billion years ago. By assembling observations of galaxies at many different distances, astronomers create a timeline of galactic evolution. It is like watching a time-lapse video of the universe growing up, from its turbulent youth to its more settled present. This is one of the most profound gifts of light years. They allow us to witness change on timescales far longer than human lifetimes, longer even than the existence of our species. We see the universe not as a static picture, but as a dynamic, evolving system. We watch stars being born, galaxies colliding, clusters forming, and the large-scale structure of the cosmos taking shape. Light from early galaxies reveals the first stars. The first stars in the universe were different from stars today. They formed from pure hydrogen and helium, with no heavier elements. Astronomers call these population 3 stars, and none have been directly observed. They lived fast and died young, exploding as supernovae and seeding the cosmos with the first carbon, oxygen, and iron. Their deaths made possible the formation of planets and life. Light from these first stars has been traveling for over 13 billion years. The galaxies containing them are so distant and faint that even the most powerful telescopes struggle to detect them. But astronomers are searching. By looking at the most distant, most highly redshifted galaxies, they hope to catch a glimpse of light from the first stellar generation, the stars that lit up the dark universe. When such light is finally detected and studied, it will tell us about the conditions in the early universe. How hot were the first stars? How massive? How quickly did they form? What elements did they create? The answers are encoded in the light, in the spectrum of wavelengths and intensities. Light years of travel preserve that information, delivering it to us intact after its immense journey. Each photon from a first-generation star has crossed nearly the entire observable universe to reach us. It has traveled through expanding space, through intergalactic voids, perhaps through wisps of gas and dust, and finally through Earth's atmosphere to strike our telescopes. In that moment, the photon completes its journey, and we receive a message from the dawn of stars themselves. The universe was once dark, before stars formed. For several 100 million years after the Big Bang, the universe was dark. No stars had yet formed. Space was filled with neutral hydrogen gas, slowly collapsing under its own gravity into clumps that would become the first galaxies. This period is called the Cosmic Dark Ages, a time between the glow of the Big Bang and the ignition of the first stars. Eventually, gravity pulled enough gas together to form the first stars. These massive stars lit up, emitting intense ultraviolet light. This light ionized the surrounding hydrogen, turning it from neutral to charged, creating bubbles of ionized gas around each star. As more stars formed, these bubbles grew and merged, eventually ionizing all the hydrogen in the universe. This is called the epoch of reionization. Light from galaxies during reionization has been traveling for over 13 billion years to reach us. By studying these galaxies, astronomers learn when the first stars formed, how quickly they ionized the universe, and what the cosmos looked like during this transformative period. The light carries direct evidence of the transition from darkness to light, from a universe without stars to one filled with them. This ancient light is incredibly faint, redshifted into the infrared, and requires the most sensitive instruments to detect. But it is there, streaming toward us across 13 billion light-years of space, carrying news of a time when the universe was just waking up. Light years measure not just distance, but the great arc of cosmic history, from darkness to dawn, to the brilliant sky we see today. Some photons have been traveling since you were born. Consider this. A photon leaving a star 100 light-years away right now will arrive at Earth in 100 years. If you were born in the year 2000, a photon that left a star 100 light-years away in that same year is arriving right now. It has been traveling your entire life, matching your journey through time as it makes its journey through space. Every moment, new photons are beginning their journeys toward us from countless stars. Some will arrive in years, some in centuries, some in millennia. And every moment, photons that began their journeys long ago are arriving, completing voyages that started before we were born, before human civilization, before humanity itself. The sky is constantly refreshing, a steady rain of ancient light. This means the stars you see tonight are different from the stars anyone has ever seen before. The configuration is the same, the constellations are unchanged, but the specific photons arriving are unique. They are new messengers bearing old news. The light that reaches your eyes tonight is light no one else will ever see. It is yours alone, a personal connection to the cosmos. In a real sense, every glance at the stars is unique. The universe is constantly revealing itself to us, photon by photon, each one completing a journey measured in light years and years of time. We are bathed in light from countless moments in history, all arriving together, overlapping in the present, painting the sky with the past. The Milky Way is 100,000 light-years across. Our home galaxy, the Milky Way, is a vast spiral containing hundreds of billions of stars. From edge to edge, it measures about 100,000 light-years. This means light from stars on the far side of the galaxy takes 100,000 years to reach the other side. The Milky Way is so large that even light, the fastest thing there is, requires 100 millennia to cross it. We live about 2/3 of the way out from the galactic center, in a spiral arm called the Orion Arm. The center of the galaxy lies about 26,000 light-years away. When we look toward the galactic center, we see it as it was 26,000 years ago. Events happening there right now will not be visible to us for another 26,000 years. This is true for every part of the galaxy. Stars in the Milky Way are separated by light years or tens of light years. The galaxy is not a single place in a single moment. It is a collection of places at different moments, all bound together by gravity, but separated by the time light takes to travel. The Milky Way is spread out in time as well as space. If a supernova exploded on the far side of the galaxy today, we would not see it for 100,000 years. Entire civilizations could rise and fall between the explosion and our observation of it. The galaxy we inhabit is larger than our lifetimes, larger than human history, larger than the history of our species. It is measured in light years, in epochs, in ages beyond our intuition. The galactic center glows 26,000 years ago. When telescopes peer toward the center of the Milky Way, they observe a dense cluster of stars orbiting a supermassive black hole. Astronomers have watched these stars for decades, tracking their orbits, measuring their speeds, and calculating the mass of the black hole. These observations show a black hole of about 4 million solar masses, sitting quietly at the galactic heart. But everything we see there is 26,000 years old. The positions of the stars, the emissions from gas falling toward the black hole, the structure of the surrounding region, all of it reflects the state of the galactic center in the distant past. If something dramatic happened there today, a sudden flare, a star being consumed, we would not know for 26 millennia. This creates a strange disconnect. Astronomers study the galactic center in real time, tracking changes year by year. But the changes they observe are not happening now. They happened long ago. The now at the galactic center is unknowable to us. We can only watch its past unfold, patient observers separated by light years of distance and years of time. The same is true for any distant object. The current state of a star 10 light-years away is unknowable. We see only its past. The star could have exploded yesterday, and we would not know until 10 years from now. The universe's present is hidden from us, fragmented across light-years of space. We live in a cosmos where simultaneity is relative, and the present is always out of reach. Andromeda is approaching despite the expansion of space. The Andromeda galaxy, despite being 2.5 million light-years away, is not receding from us like most galaxies. It is approaching. While the universe expands and carries distant galaxies away, Andromeda and the Milky Way are bound by gravity, pulling each other closer. They are on a collision course, fated to merge in about 4 billion years. This approach is measurable. By studying the spectrum of light from Andromeda, astronomers detect a blue shift instead of a redshift. The light is compressed, shifted toward shorter wavelengths, because Andromeda is moving toward us at about 110 kilometers per second. In cosmic terms, this is not especially fast, but over billions of years, it adds up. When the collision occurs, it will be slow and majestic. Stars are so far apart that actual collisions between them will be rare. But the gravitational interaction will distort both galaxies, throwing stars into new orbits, triggering bursts of star formation, and eventually merging the two spirals into a single large elliptical galaxy. Astronomers call the result Milkomeda, or sometimes Milkdromeda. The light we see from Andromeda tonight is 2.5 million years old. The galaxy approaching us is not the Andromeda we observe, but the Andromeda that exists now, unknowable and unseen. We see its past hurtling toward us, a promise of a future collision written in light years and gravity. The cosmos unfolds on timescales that dwarf our own, measured in epochs of light. Light years help us find exoplanets. In recent decades, astronomers have discovered thousands of planets orbiting other stars. These exoplanets are detected through various methods, many of which rely on light. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. This is called a transit, and by measuring the dimming, astronomers can infer the planet's size and orbit. The light we observe during a transit is, of course, not happening now. If a star is 100 light-years away, the transit we see tonight occurred 100 years ago. We are watching the past unfold, observing a planet that crossed in front of its star a century ago. The planet's current position is unknown to us. We see only where it was, long ago. This does not diminish the discovery. We are still learning about real planets orbiting real stars, but it reminds us that all astronomy is historical. When we study exoplanets, we study their pasts. When we search for signs of life in their atmospheres by analyzing starlight filtered through alien air, we search for life as it was, not as it is. If we detect biosignatures in the atmosphere of a planet 100 light-years away, we will have found evidence of life that existed a century ago. Whether that life still exists is unknowable. If a civilization on that planet is trying to communicate, their signals will take 100 years to reach us, and our reply will take another 100 years to reach them. Light years separate not just places, but entire histories. Voyager 1 has barely left the solar system. Voyager 1, launched in 1977, is the most distant human-made object. It has traveled farther from Earth than anything else we have ever built. As of today, it is over 24 billion kilometers away, in interstellar space beyond the influence of the Sun's solar wind. This is an astounding achievement, a testament to human ingenuity and ambition. And yet, in light years, Voyager 1 has traveled only about 0.0025 light years, not even 0.25% of a single light year. Light covers in about 20 hours what Voyager 1 has taken over 45 years to travel. The spacecraft is moving at 17 kilometers per second, an incredible speed by human standards, but utterly insignificant compared to the speed of light. If Voyager 1 were headed toward Proxima Centauri, the nearest star, it would take over 70,000 years to arrive. The spacecraft would need to cross 4.2 light-years of empty space, and at its current speed, it simply cannot do it in any time frame relevant to human civilization. Light makes the journey in 4 years. Voyager 1 would need millennia. This comparison shows why light-years are the only practical measure for cosmic distances. Human spacecraft, even at their fastest, are hopelessly slow compared to light. We cannot travel to the stars in human lifetimes, not with our current technology, but light can. And by studying the light from distant stars, we reach them in a sense, connecting across light years through photons that make the journey we cannot. Light years reveal the difficulty of interstellar travel. Science fiction often depicts starships traveling between stars in days or weeks. In reality, the distances are so vast that even traveling at a significant fraction of light speed would require decades or centuries. The nearest stars are light years away, and there are no convenient shortcuts. Space is mostly empty, and crossing it takes time. To reach Proxima Centauri in 40 years would require traveling at about 10% of light speed. This is far beyond our current capabilities. The fastest spacecraft we have ever built, the Parker Solar Probe, reaches speeds of about 0.06% of light speed at its closest approach to the Sunday. To achieve 10% would require technologies we do not yet possess, enormous amounts of energy, and solutions to countless engineering challenges. And 40 years is just to the nearest star. Most stars are tens, hundreds, or thousands of light years away. To explore the galaxy would require voyages lasting thousands or millions of years, unless we discover new physics that allows faster-than-light travel. The light years separating stars are barriers, vast and daunting, reminding us that the cosmos is not easily conquered. Yet light makes the journey effortlessly. Photons from distant stars reach us constantly, bringing information, beauty, and knowledge. We may never travel to those stars ourselves, but their light travels to us. In this way, we explore the universe without leaving home. Light years are both a measure of what separates us and a measure of what connects us to the wider cosmos. Imagining a journey at light speed. Imagine, for a moment, that you could travel at the speed of light. You board a spacecraft, accelerate instantly to 300,000 kilometers per second, and point toward the stars. What would you see? What would you experience? The journey would be unlike anything possible in ordinary life, a voyage through space and time itself. From your perspective, something strange would happen. Time dilation, predicted by Einstein's relativity, would compress your experience of time to zero. At light speed, no time passes for you. Your journey, no matter how many light years it covers, would feel instantaneous. You would arrive at your destination in the same moment you left, experiencing nothing in between. The universe outside would age, but you would not. For observers watching you from Earth, the journey would unfold normally. If you traveled to a star 10 light years away, they would see you depart and then wait 10 years before learning you had arrived, as the news traveled back at light speed. From their perspective, you would age slowly during the trip, time passing more slowly for you than for them, though still passing. But from your perspective, no time would pass at all. This paradox is resolved by relativity. Time is not absolute. It flows differently for observers in different states of motion. At light speed, time stops for the traveler. The light years of distance collapse into nothingness. But this is impossible for anything with mass. Only light itself, massless and eternal, can travel at light speed. For us, made of matter, light speed remains forever out of reach. Nothing with mass can reach light speed. The speed of light is a cosmic speed limit, unbreakable by any object with mass. As you accelerate toward light speed, you gain energy. But that energy does not only increase your velocity, it also increases your mass. The faster you go, the heavier you become, and the more energy it takes to accelerate further. Approaching light speed requires infinite energy, which is impossible. This is not a technological limitation. It is a fundamental law of physics. The universe is structured such that light speed is a boundary, a limit that matter cannot cross. Photons reach this speed effortlessly because they have no mass. Electrons, atoms, spacecraft, anything made of matter can only approach light speed asymptotically, getting closer and closer, but never quite arriving. Even reaching 99% of light speed would require staggering amounts of energy. At that speed, relativistic effects become dramatic. Time would slow, distances would contract, and the traveler's mass would increase by a factor of 7. To go faster requires even more energy, and the returns diminish rapidly. Reaching light speed is not a matter of better engines. It is impossible in principle. This is why light years represent such vast distances for material beings. Light crosses them easily, but we cannot. We are bound by our mass, by the structure of space-time itself. The universe allows information to travel at light speed in the form of photons, gravitational waves, and other massless phenomena. But matter must travel more slowly, making the light years between stars formidable obstacles to physical exploration. Time dilation affects travelers at high speed. Even at speeds far below light speed, relativistic effects begin to emerge. If a spacecraft could travel at 50% of light speed, time aboard the ship would pass more slowly than time on Earth. A journey to a star 10 light-years away would take 20 years from Earth's perspective, but only about 17 years for the travelers. The difference is subtle, but real. At 90% of light speed, the effect becomes dramatic. Time aboard the spacecraft would pass less than half as fast as time on Earth. A 20-year journey from Earth's perspective would feel like only about 9 years to the travelers. They would age more slowly, their clocks would tick more slowly, and every process aboard the ship would unfold at a reduced rate compared to the outside universe. This is not an illusion or a trick of perception. It is a real physical effect. Time genuinely passes at different rates for observers in different states of motion. This has been confirmed through countless experiments, from atomic clocks on aeroplanes to particle accelerators, where subatomic particles live longer than expected because they are moving so fast. Time is flexible, shaped by motion and gravity. For interstellar travelers, this could be advantageous. By traveling at high speeds, they could cross vast distances while aging relatively little. But they would return to find Earth much older than they expected. Light years of distance would translate into decades or centuries of time passing at home. They would be time travelers, moving into the future by traveling through space at relativistic speeds. The twin paradox illustrates time dilation. A famous thought experiment called the twin paradox illustrates these effects. Imagine two twins, one who stays on Earth and one who travels to a distant star and back at relativistic speed. When the traveling twin returns, less time has passed for them than for the twin who stayed home. The traveler is younger, having aged less during the journey. This seems paradoxical because motion is relative. Why is the traveler younger and not the stay-at-home twin? The resolution is that the traveling twin experienced acceleration and deceleration, changing direction to return home. This breaks the symmetry. The traveler moved through spacetime along a different path, and that path was shorter in terms of proper time, the time experienced by the traveler. If the twin traveled to a star 10 light-years away at 90% of light speed, the journey would take about 22 years from Earth's perspective, 11 years out and 11 years back, but the traveling twin would age only about 9 years in total. Returning home, they would find their twin 13 years older. The light years crossed in space translated into years of difference in time. This is not science fiction. It is a prediction of relativity, confirmed by experiment. Time is not a universal river flowing at the same rate for everyone. It is personal, shaped by motion and gravity. Light years measure not just distance through space, but potential differences in the flow of time. The cosmos is stranger and more wonderful than everyday experience suggests. Communication across light years is slow. Imagine a civilization on a planet orbiting a star 100 light-years away. If they send us a message today, a radio signal carrying information across space, that message will take 100 years to arrive. We will not receive it until the year 2125, and if we reply immediately, our response will take another 100 years to reach them, arriving in the year 2225. A simple exchange, a message and a reply, would take 200 years. A conversation would be impossible. By the time we received their message and sent a reply, centuries would have passed. Entire generations would come and go between each exchange. Any dialogue would unfold over timescales longer than human lifetimes, perhaps longer than civilizations themselves endure. This is one of the profound implications of light years. They isolate civilizations from each other. Even if the galaxy teems with intelligent life, the vast distances make communication agonizingly slow. Radio waves, like light, travel at light speed. There is no way to send information faster. Every message must cross the light years, requiring years or centuries or millennia to arrive. This creates a lonely universe, where civilizations are scattered like islands in an endless ocean, separated by gulfs of space so vast that even their voices take ages to cross. We send signals into space, hoping someone will hear. But if anyone answers, we will not know for decades or centuries. The light years that show us the beauty of the stars also enforce a cosmic isolation. The search for extraterrestrial intelligence faces light-year delays. The search for extraterrestrial intelligence, or SETI, scans the skies for signals from other civilizations. Radio telescopes listen for patterns that could not be natural, structures in radio noise that might indicate intelligent design. So far, no confirmed signals have been detected. The universe remains silent, or at least appears so from our vantage point. But even if SETI succeeds, the implications are strange. Any signal we detect will be old, having traveled across light years to reach us. If we detect a signal from a civilization 1,000 light years away, we are hearing them as they were 1,000 years ago. Their current state is unknown. They may have advanced, they may have fallen, they may no longer exist. We would be listening to history, and if we send a reply, it will take another 1,000 years to reach them. By the time they receive our message, 2,000 years will have passed since they sent theirs. This is not a conversation. It is an exchange of time capsules, messages sent into the future, hoping someone will still be there to receive them. The light years make any interaction profoundly asynchronous. This does not make SETI worthless. Detecting any signal would be revolutionary, proof that we are not alone, but it would not lead to dialogue in any meaningful sense. It would lead to knowledge, history, archaeology of a sort. studying the ruins of messages sent long ago. The light years that let us see distant stars also ensure that any contact with extraterrestrial intelligence will be slow, patient, and deeply historical. Colonizing the galaxy would take millions of years. If humanity ever spreads beyond Earth, truly colonizing other star systems, the process would unfold over unimaginable timescales. Even traveling at a substantial fraction of light speed, reaching nearby stars would take decades. Establishing self-sufficient colonies would take longer. Expanding to more distant stars would require centuries or millennia. Filling the galaxy would take millions of years. Each colony would be isolated by light years from every other. Communication would be slow, travel even slower. A message sent from one colony to another might take decades or centuries to arrive. A traveler journeying between stars might arrive to find the civilization they left has changed beyond recognition. The galaxy would not be a unified human civilization. It would be a scattered archipelago of independent worlds. This isolation is enforced by light years. No matter how advanced technology becomes, unless new physics allows faster-than-light travel or communication, the speed of light remains a barrier. Light years will always mean years of travel time, years of communication delay, years separating events from their observation. The structure of spacetime itself imposes this limitation. Some scientists have speculated about wormholes, hypothetical tunnels through spacetime that could connect distant points without crossing the space between. If such things exist and can be traversed, they could overcome the light-year barrier, but they remain purely theoretical. As far as we know, light years are the true measure of cosmic distance, and crossing them requires time, patience, and generations of effort. The Fermi paradox questions why we see no one. Given the vast number of stars in the galaxy, many with planets, some of which might harbor life, where is everyone? This question, posed by physicist Enrico Fermi, is called the Fermi paradox. If intelligent life is common, the galaxy should be teeming with civilizations. Some should have arisen millions of years ago. Why have they not colonized the galaxy? Why do we see no signs of them? One possible answer involves light years. The distances are so vast, the timescales so long, that even a spacefaring civilization might take millions of years to spread across the galaxy. We have only been looking for signals for a few decades. We have only been capable of spaceflight for less than a century. Perhaps we are simply too young, too isolated, too far from other civilizations to have detected them yet. Or perhaps the light-year barrier is too great. Perhaps most civilizations never develop interstellar travel. Perhaps they remain confined to their home systems, separated from each other by distances that are easy to observe across, but nearly impossible to cross. Perhaps the galaxy is full of civilizations, all isolated, all looking outward, all wondering why the universe seems so empty. The Fermi paradox has many proposed solutions, but the vastness measured in light years is central to many of them. The universe is so large, the distances so immense, that even a galaxy containing millions of civilizations might still seem empty to each one. Light years separate us not just from stars, but potentially from neighbours we cannot yet see or reach. Light years show us the universe is mostly empty. When you look at the night sky, it seems full of stars, but the distances between them are staggering. The average distance between stars in our region of the galaxy is about 5 light years. That means if you could shrink the sun to the size of a grain of sand, the nearest star would be another grain of sand about 5 kilometres away. The space between is almost entirely empty. On larger scales, the emptiness is even more striking. The distance between galaxies is millions of light-years. Between galaxy clusters, the voids are hundreds of millions of light-years across. These voids contain almost nothing. No stars, no galaxies, just a few stray atoms per cubic meter. The universe is overwhelmingly empty, with matter concentrated into tiny pockets separated by vast gulfs. Light-years quantify this emptiness. They show us that the universe is not a crowded place. It is spacious, beyond comprehension. Most of space contains nothing but a faint whisper of matter and the background radiation left over from the Big Bang. The stars, planets, and galaxies, all the structure we see, occupy only a tiny fraction of the total volume of the cosmos. This emptiness is not a defect, it is a feature. The expansion of the universe has spread matter thin, creating the vast distances measured in light-years. These distances allow light to travel freely, carrying information across the cosmos. They also create the silence and isolation that characterize existence on cosmic scales. We are islands in an ocean of space, separated by light-years from any other shore. The concept of now is meaningless on cosmic scales. On Earth, we share a common present. When something happens in one place, we can know about it in another place almost instantly, or at least within seconds, through communication technology. The concept of now seems obvious, but on cosmic scales, now loses its meaning. Light speed is finite, and information takes time to travel. There is no universal present moment. Consider two events, one happening on Earth and one happening on a star 10 light-years away, that both occur now by our clocks. From our perspective, they are simultaneous. But an observer moving toward that star at high speed would see the event on the star as happening first. An observer moving away from that star would see it as happening second. Simultaneity is relative, not absolute. This means there is no objective answer to the question, what is happening right now on Andromeda? From our reference frame, right now on Andromeda is an event that will be visible to us in 2.5 million years. But from a different reference frame, a different answer would be correct. The concept of a universal present moment, of everything happening now, is an illusion of our limited perspective. Light-years enforce this relativity of simultaneity. Because light takes time to travel, and because time itself is relative, there is no way to define a cosmic now. The universe does not have a single present moment shared by all observers. It has countless present moments, one for each observer, depending on their motion and position. The only shared reality is the past, the events whose light has already arrived. The observable universe has edges defined by light. The observable universe is not the entire universe. It is the portion of the universe from which light has had time to reach us since the Big Bang. This creates a sphere around us, with Earth at the center, roughly 93 billion light-years in diameter. Beyond this boundary, light has not yet reached us. We cannot see it, and we never will, if the expansion of space continues to accelerate. This boundary is constantly expanding as light from more distant regions has time to arrive. But because space itself is expanding, some regions are moving away faster than light can approach. These regions will never become visible to us. The observable universe is both growing and, in a sense, shrinking as distant galaxies accelerate beyond the horizon. The edge of the observable universe represents a limit of knowledge. We cannot see beyond it, not because there is nothing there, but because the light has not reached us. It is a horizon, not a boundary in space, but a boundary in time. We are surrounded by this horizon at every point, defining what is knowable and what is forever hidden. Light-years define this horizon. The observable universe is approximately 13.8 billion light-years in radius in terms of light travel time. But because space has expanded during the journey, the actual distance to the edge is greater, roughly 46.5 billion light-years. This is the farthest we can see using light. It is the ultimate measure of our cosmic neighborhood. Dark energy accelerates the expansion beyond light speed. In the late 1990s, astronomers discovered that the universe's expansion is accelerating. Something called dark energy is pushing space apart faster and faster. This acceleration means that distant galaxies are receding from us at ever-increasing speeds. The most distant galaxies are already moving away faster than light speed, carried by the expansion of space itself. This does not violate relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. Galaxies embedded in that space are carried along, and the distance between us and them can grow faster than light could cross it. This means light from the most distant galaxies is fighting a losing battle, trying to reach us across space that is expanding faster than the light can travel. Some of this light will eventually reach us, but only light that is already close enough. Light from galaxies beyond a certain distance will never reach us, no matter how long we wait. The expansion will always carry them away faster than the light can approach. These galaxies are beyond the cosmic horizon, forever unreachable, their light permanently lost to us. Dark energy, whatever it is reshaping the future of light years. As time goes on, more and more galaxies will cross beyond the horizon. The observable universe will eventually contain fewer galaxies as they accelerate beyond reach. Billions of years from now, observers in our galaxy will see a lonelier universe, with only the closest galaxy clusters remaining visible. The light years that once connected us to distant galaxies will have been stretched into unbridgeable gulfs. Future astronomers may see a darker sky. Imagine astronomers billions of years in the future, long after the sun has died, observing from whatever remains of our galaxy or its merger with Andromeda. They will look out and see fewer galaxies. Most will have accelerated beyond the horizon, their light no longer able to reach the observer. The cosmic microwave background will have redshifted into undetectability. These future observers, if they exist, might not discover the Big Bang. They might not realize the universe had a beginning, or that it is expanding. The evidence, carried by light across light years of space, will have faded beyond detection. They might think the universe is static and eternal, containing only the local group of galaxies, surrounded by darkness. This thought is haunting. It suggests that our current era is special. We live at a time when the evidence of the Big Bang is still visible, when distant galaxies can still be observed, when the history of the universe can still be read from the light reaching us. Future civilizations may not have this opportunity. The light years that currently deliver information will eventually fail to bridge the growing distances. It also suggests that there may be aspects of the universe we cannot observe because we live too late. Perhaps earlier epochs had evidence that has already faded beyond our horizon. Perhaps the universe contains structures or events that happened so long ago and so far away that their light will never reach us. We see much, but we cannot see everything. The observable universe is a window, and that window is closing. Gravitational lensing bends light across light years. Gravity bends light. Massive objects like galaxy clusters warp the fabric of spacetime, and light traveling through that warped space follows curved paths. This effect, predicted by Einstein and confirmed by observation, is called gravitational lensing. It allows astronomers to see objects that would otherwise be hidden or too faint to detect. When a massive galaxy cluster lies between us and a more distant galaxy, the cluster's gravity bends the light from the distant galaxy, magnifying and distorting it. Sometimes, multiple images of the same galaxy appear, stretched into arcs or rings. This lensing reveals galaxies billions of light-years away that would otherwise be invisible. The light from these galaxies has been traveling for billions of years, bent and focused by intervening mass. Gravitational lensing also creates time delays. Light, taking different paths around a lensing object, arrives at different times. If the distant galaxy has a variable event, like a supernova, we might see it multiple times, each image showing the event at a slightly different moment. The light has traveled the same distance in light-years, but taken different routes through curved spacetime, arriving at different times. This bending of light across light-years reveals the mass distribution of the universe. By studying how light is lensed, astronomers map the invisible dark matter that fills galaxy clusters. They weigh the universe, tracing the gravitational influence of matter we cannot see directly. Light, patient and persistent, carries information not just about its source, but about everything it passes through on its long journey. The cosmic light horizon surrounds every observer. Every observer in the universe is surrounded by their own light horizon, the boundary of what they can see. For us, that boundary is roughly 46.5 billion light-years away in every direction. But an observer in a distant galaxy has a different horizon, centered on their location. Parts of our observable universe are beyond their horizon, and parts of theirs are beyond ours. This means different observers see different portions of the universe. There is overlap, of course. We share much of the observable universe with nearby galaxies. But galaxies billions of light-years away, on opposite sides of our observable universe, cannot see each other. The light from one has not had time to reach the other. They are mutually invisible, separated by distances so vast that light itself cannot bridge them in the age of the universe. This creates a strange situation. The universe may be much larger than any observer can see. It may even be infinite. But each observer is limited to their own light horizon, a bubble of visibility surrounding them. Beyond that bubble, the universe continues, but unknowably. Other regions, other galaxies, other structures exist, but we can never observe them because the light will never arrive. The light horizon is not a physical barrier. It is a consequence of light having a finite speed and the universe having a finite age. Light can only travel so far in the time that has passed since the Big Bang. This creates a natural limit on knowledge, a boundary beyond which information cannot reach us. We are, in a sense, trapped inside our own light cone, able to observe only the past of regions whose light has reached us. Every photon carries a history. When a photon arrives at your eye or telescope, it has completed a journey. That journey may have lasted years, centuries, or billions of years. Along the way, the photon has traveled through space that was expanding, through regions of different density, perhaps through gas clouds or around gravitational lenses. Each part of the journey left subtle marks on the photon. The photon's wavelength tells you about its source and its journey. If it has been redshifted, you know it came from far away, across expanding space. If it is blue or ultraviolet, you know it came from a hot source. If its spectrum shows absorption lines, you know it passed through gas that absorbed specific wavelengths, revealing the composition of that gas. Every photon is an archive. By studying photons carefully, astronomers reconstruct not just the source, but the journey. They learn about the density of gas between us and distant galaxies, about the distribution of matter, about the rate of expansion, about the conditions in the early universe. Light is not just a signal. It is a historian, carrying information about everything it has encountered across its light years of travel. This is why astronomers speak of photons as messengers. Each one brings news from distant places and ancient times. Each one tells a story, if you know how to read it. The light years they have crossed are not just empty space. They are filled with subtle influences that shape the light, encode information, and allow us to learn about the universe through which the photons have traveled. Light can be stored and delayed. In laboratories, scientists have found ways to slow light down, trapping it in specially prepared materials. Light moving through these materials travels much slower than it does in vacuum, sometimes reduced to walking speed or even brought to a complete halt. This does not violate the fundamental speed limit. Light in vacuum always moves at light speed, but in matter, it can be slowed. This slowing occurs because photons are absorbed and re-emitted by atoms in the material. The photons themselves still travel at light speed between atoms, but the repeated absorption and emission delay their progress. The result is an effective speed slower than light speed. In extreme cases, light can be stopped entirely, stored in atomic states, and then released later. These experiments do not help with astronomical light years. We cannot slow down light from distant stars, but they reveal the flexibility of light's behavior and the ways matter and energy interact. They also demonstrate that light speed as a cosmic speed limit applies to light in vacuum. In other contexts, light can behave in surprising ways, constrained by the properties of the medium through which it moves. For astronomical purposes, light travels unimpeded across the vast empty spaces between stars and galaxies. The near vacuum of space allows photons to maintain their speed for billions of years, crossing light years without slowing. This is why astronomical observations are possible. If space were filled with material that slowed light, the photons would never reach us, or would arrive so delayed and scattered that we could learn nothing from them. Cosmic rays are not light, but travel nearly as fast. While light crosses the universe, so do cosmic rays, high-energy particles like protons and atomic nuclei, accelerated to nearly the speed of light by violent events. These particles travel for light years across space, sometimes colliding with Earth's atmosphere and creating showers of secondary particles. They are not light, but they are messengers of a different kind. Cosmic rays carry information about their sources. The most energetic ones come from outside our galaxy, perhaps from supermassive black holes or colliding galaxies. Their energies are astonishing, far beyond anything achievable in human-made particle accelerators. Studying them reveals processes we cannot replicate on Earth, extreme physics occurring in the most violent corners of the universe. But cosmic rays have a problem light does not. They are charged particles, and charged particles are deflected by magnetic fields. As they travel across light years of space, passing through the tangled magnetic fields of the galaxy, their paths bend and twist. By the time they reach Earth, their direction no longer points back to their source. They arrive from all directions, their origins scrambled. Light, being uncharged, travels in straight lines unless bent by gravity. This makes it a far better messenger for astronomy. We can trace a photon back to its source, learning where it came from. Cosmic rays, despite traveling nearly as fast and carrying tremendous energy, cannot tell us where they originated. They are anonymous messengers, their histories erased by the magnetic fields they encountered across the light years. The speed of light is the speed of causality. Light speed is not just the speed at which light travels, it is the speed at which cause and effect propagate through the universe. Nothing can influence something else faster than light speed. If an event occurs here, its influence cannot reach another location until light would have had time to travel there. This is the speed of causality, the maximum rate at which information and influence spread. This means the universe has a fundamental structure to its events. If two events are separated by more light years than the time between them allows light to cross, they cannot influence each other. They are causally disconnected, existing in each other's future or past but not in each other's present. The light cone, the region that can be reached by light, defines what events can affect what other events. On Earth, this structure is invisible because light crosses planetary distances so quickly. But on cosmic scales, it shapes everything. The universe is not a single interconnected now. It is a web of causally connected regions, each able to influence only what light can reach. Beyond that, events are independent, unfolding without knowledge of each other, separated by the light years that prevent communication. This is why faster-than-light travel or communication would be so revolutionary. It would violate causality, allowing effects before causes, paradoxes, and contradictions. Most physicists believe this is impossible, that the structure of space-time forbids it. Light years are not just distances to be crossed. They are fundamental features of how the universe is organized, how events relate to each other, how reality is structured. Relativity connects space and time through light. Einstein's theory of relativity rests on the constancy of light speed. Light always travels at the same speed through vacuum, regardless of the motion of the source or observer. This simple fact, confirmed by experiment, led to a revolution in physics. Space and time, previously thought to be separate, were revealed to be aspects of a single entity, spacetime. In spacetime, distances are measured not just in space but in time. Light years capture this perfectly. A light year is a distance in space equal to the distance light travels in a year of time. Space and time are interchangeable through the speed of light. Moving through space is like moving through time, and the two are unified into a four-dimensional structure. This unification explains why observers in different states of motion experience time differently. They are moving through space-time along different paths. A traveler moving at high speed takes a different route through space-time than someone at rest, and that route involves less passage of proper time. The light years they cross in space correspond to differences in the time they experience. Relativity also explains why light speed is a limit. Moving faster than light would be like moving backward in time, violating causality. The structure of space-time forbids it. Light speed is woven into the fabric of reality, a fundamental constant that shapes everything. Light years are not arbitrary. They are measurements of space-time itself, distances expressed through the only speed that is absolute and universal. The universe began as a point smaller than a light year. 13.8 billion years ago, the universe began. In the first instance, all of space, all of matter, all of energy, everything that would eventually become the vast cosmos, was compressed into a region smaller than an atom. There were no light years yet. Space itself was newborn, tiny, dense, and hot beyond imagination. In those first moments, the universe expanded faster than light speed. This is allowed because space itself can expand at any rate. What cannot exceed light speed is motion through space. But space can grow, stretch, and carry matter with it at any velocity. In a fraction of a second, the universe inflated from smaller than a proton to larger than a galaxy. This is called cosmic inflation. As inflation ended, the universe continued expanding, but more slowly. Light could now move freely, though for the first few 100,000 years, space was opaque, filled with plasma that scattered photons. Only when the universe cooled and atoms formed did light begin to travel across space. The first light years came into being as distances grew and photons began their journeys. From that tiny beginning, the universe has expanded to its current immensity. The observable universe spans 93 billion light-years. The distances between galaxies are millions or billions of light-years. The scales are incomprehensible compared to the pinpoint of space where it all began. And yet, every light-year of space, every photon crossing it, traces back to that moment, that infinitesimal origin. Light from the Big Bang surrounds us, the cosmic microwave background. The faint glow left over from the Big Bang is visible in every direction. It comes from the moment the universe became transparent, about 380,000 years after the beginning. At that time, the universe was roughly 1/1000th of its current size. Light released then has been traveling ever since, stretched by expansion into microwaves. This light has been traveling for over 13 billion years. It has crossed the entire observable universe to reach us. When we detect the cosmic microwave background, we are observing the most distant light possible, the edge of the observable universe itself. We are seeing the universe as it was in its infancy, glowing uniformly in every direction. The cosmic microwave background is a sphere surrounding us, but not a sphere in space. It is a sphere in space-time, the boundary of the observable universe. Every point on that sphere is the same distance away, in terms of light travel time, about 13.8 billion light-years. But because space has expanded, the actual distance is much greater, roughly 46.5 billion light-years. This ancient light connects us to the beginning of time. It is a message from the dawn of the universe, carried across light-years and eons to arrive in our telescopes today. By studying its tiny temperature variations, astronomers map the early universe, revealing the seeds of galaxies, the density fluctuations that grew into all the structure we see. The cosmic microwave background is the ultimate light-year journey, spanning nearly the entire age of the cosmos. Supernovae reveal the acceleration of the universe. In the late 1990s, two teams of astronomers studied distant Type Ia supernovae, using them as standard candles to measure cosmic distances. They expected to find that the universe's expansion was slowing, decelerated by the mutual gravity of all the matter within it. Instead, they found something shocking. The expansion was accelerating. Distant supernovae, billions of light-years away, appeared fainter than expected. This meant they were farther away than they should have been if the universe were simply coasting. Space was expanding faster now than it was when that light was emitted billions of years ago. Something was pushing the universe apart, accelerating the expansion against gravity. This discovery revealed dark energy, a mysterious force or property of space itself that drives the acceleration. Dark energy makes up about 70% of the universe's total energy. We do not know what it is, only that it exists and that it is causing the universe to expand faster and faster. The light years between galaxies are growing at an accelerating rate. The supernovae that revealed this are billions of light years away. Their light has been traveling for billions of years, carrying information about the universe as it was in the past. By observing supernovae at different distances and therefore at different times, astronomers traced the expansion history of the universe, discovering that acceleration began roughly 5 billion years ago. Light from across light-years of space rewrote our understanding of the cosmos. The fate of the universe depends on dark energy. If dark energy continues to dominate, the universe will expand forever, accelerating without end. Galaxies will move farther and farther apart. Eventually, all galaxies outside our local group will recede beyond the horizon, their light unable to reach us. the universe will become darker, lonelier, colder. Stars will exhaust their fuel, black holes will evaporate, and in the unimaginably distant future, space itself may be all that remains. This scenario is called the Big Freeze, or heat death. The universe does not end in a dramatic collapse, but fades away into cold, dark, empty space. Light years will continue to grow, distances increasing without limit, until the universe is so diffuse that nothing remains but empty space stretched across incomprehensible distances. Alternatively, dark energy could change. If it weakens, gravity might eventually halt the expansion and pull everything back together in a big crunch, the opposite of the Big Bang. If dark energy strengthens, it could tear galaxies, stars, and eventually atoms apart in a big rip. These are speculative, but the point is clear. The future of the universe depends on how dark energy behaves, and light years are the measure of that future. For now, observations suggest a big freeze. The universe will expand forever, and the light years separating galaxies will grow without bound. Future observers, if any exist, will see fewer and fewer galaxies until only the local cluster remains. The light from distant galaxies, traveling across light years of space, will fade into the void, stretched beyond detection by the relentless expansion. Our view of the universe is constantly updating. Every moment, new photons arrive from across the universe, bringing fresh information. The sky is not static. It is constantly refreshing. A stream of light carrying news from different distances and different times. Nearby stars show us the recent past. Distant galaxies show us the ancient past. Together, they paint a picture of the universe as it was across time. Astronomers take advantage of this by observing over time. Variable stars change brightness. Supernovae flare and fade. Galaxies collide and merge. By watching the sky for years or decades, astronomers see these changes unfold. But remember, the changes they see are not happening now. They happened long ago, and the light is only just arriving. This continuous update means our knowledge of the universe is always improving. New light arrives, carrying information about events we have not seen before. Telescopes scan the sky, cataloging objects, measuring distances, and studying light from across the light years. Each observation adds to our understanding, building a more complete picture of the cosmos. The sky you see tonight is different from the sky anyone has ever seen. Not in arrangement, but in the specific photons arriving. The light reaching your eyes is unique, a moment in the endless stream of photons crossing space. Tomorrow night, new photons will arrive, continuing the story. The universe reveals itself slowly, one light year at a time, one photon at a time. Light years are a bridge between the human and the cosmic. We measure our lives in years, decades if we are fortunate. A century is a long human lifespan, but light years stretch far beyond human scales. A single light year is longer than recorded history, longer than civilization, longer than humanity has existed as a species. Light years are the realm of stars, of galaxies, of the cosmos itself. And yet, we understand them. We can imagine them, calculate them, observe their effects. Through science and mathematics, through the patient accumulation of knowledge, humans have reached beyond our brief lives to grasp the immensity of the universe. Light years are both utterly alien to human experience and deeply familiar, a concept we have made our own. This is the power of understanding. We cannot travel light years. We cannot live long enough to see a photon complete its journey from a distant star. But we can comprehend what a light year means. We can trace the path of light across the cosmos, understand the time it takes, and use that understanding to explore the universe. Light years bridge the gap between our smallness and the vastness around us. When you look at a star and know it is 10 light years away, you are connecting your brief existence to a journey 10 years long, to a star that may be billions of years old, to a photon that has traveled farther than you will ever go. In that moment, you touch the infinite. Light years are not just measurements, they are invitations to wonder, to imagine, to understand our place in a universe far grander than ourselves. Conclusion: light years illuminate our place in the cosmos. Light years are more than units of distance. They are the language of the universe. The way we speak about the immense scales of space and time that define existence beyond Earth. Every light year represents a year of light's journey, a connection between distant places and different times, a thread in the vast tapestry of the cosmos. When you see a star, you are seeing its past. The photon that reaches your eye has traveled across light years of empty space, carrying information about a sun that may have changed or died since the light began its journey. You are a witness to history, an observer of events long past, connected across the void by the patient stream of light. The universe is vast, the distances are incomprehensible, the timescales stretch beyond imagination, but light crosses those distances faithfully, bringing us knowledge, beauty, and connection. Through light years, we learn about the birth of stars, the death of galaxies, the expansion of space, and the history of everything. We see not just where things are, but when they were. As you lie here, breathing slowly, drifting towards sleep, imagine the photons that have crossed light years to reach you tonight. Imagine the stars whose light left them when your grandparents were young, when the Romans built their empire, when dinosaurs walked the earth. Imagine the galaxies whose light has been traveling for millions or billions of years. Light from a universe younger and stranger than the one we know. Light years connect us to all of it. They show us that we are part of something unimaginably vast, ancient, and beautiful. We are made of atoms, forged in stars, bathed in light that has traveled across the cosmos, living on a small world in a quiet corner of an ordinary galaxy among billions. We are both insignificant and precious, tiny and connected, brief and part of something eternal. The light that surrounds us has always been there, streaming across space, waiting to be seen. The stars have always been shining, their photons beginning journeys that may last years or centuries before finding an eye to witness them. And we, for this brief moment, are here to see them, to understand them, to marvel at the light years they have crossed. Let the calm of this understanding wash over you. Let the vastness become not frightening but peaceful. You are held by the same laws that govern the stars, made of the same matter, seeing the same ancient light. You are part of the universe, and the universe is part of you. The light years that separate you from distant suns also connect you to them, binding everything together in a web of light and time. As you close your eyes, picture the night sky above. See the stars scattered like diamonds against the dark, each one a distant sun, each one separated from you by light years of space and years of time. See the Milky Way arching overhead, a band of light from billions of stars within our own galaxy. See the faint smudge of Andromeda, an entire galaxy visible to the naked eye, 2.5 million light-years away. Know that the light you imagine seeing has traveled all those years to reach this moment. Know that new photons are always arriving, always completing their journeys, always bringing news from the cosmos. Know that you are witnessing the universe as it unfolds across time, layer by layer, light year by light year, revealing its history in the glow of stars. Let this knowledge bring you peace. Let it quiet your thoughts. Let it remind you of your place in something larger, something beautiful, something that stretches across light years and eons, but is here, now, visible to anyone who looks upward and wonders. The universe is speaking to you in the language of light, and light years are the words it uses to tell its story. Breathe deeply. Relax. Allow yourself to drift into sleep, carried by the gentle understanding that you are part of a cosmos vast beyond imagination, but present in every beam of starlight, every photon crossing space, every light year connecting the distant past to your present moment. Good night, rest well, and may your dreams be filled with the soft glow of stars whose light has traveled light years to reach you.